那这一场我很荣幸跟各位引荐Daniel J. Bernstein 跟 Tanya Langer 两位教授。那他们是世界上有属的密码学家，那也是所谓后量子密码学名称的共同发明人这样。那今天他就是要来告诉我们后量子密码学，这个东西为什么我们需要研究它？那现在的研究又是什么样子？那在演讲结束之后，如果你的问题想要用中文提出是 OK 的，那我们可以帮你翻译。好的，那我们现在就把讲台交还给讲者。
All right, thank you. Uh-oh, are we on? Yeah. Thanks for the introduction. Cryptography is about people communicating. We have names for these people. Imagine one person named Alice sending a message to another person named Bob. So here's pictures of Alice and Bob. And they're communicating through the internet or through some network. They're very long distance away from each other. And that makes a problem. The problem is that somebody's listening to the network. That's an eavesdropper. And we have a name for the eavesdropper. The eavesdropper, there's Alice and Bob communicating. The eavesdropper is someone named Eve. Here's a picture of Eve. It's a great picture. Everybody, one hand on the laptop, one hand on the mouse. Look at the camera, look at the screen, and then everybody. Okay, so Eve is listening to the connection, and Eve is maybe changing the data, changing the messages on the connection. So cryptography tries to protect against this. And the way cryptography does this is it writes messages in a secret language. Cryptography means secret writing. So cryptography changes the messages that we send in some secret way, and then sends the modified messages, and then it's supposed to protect us against the eavesdropper. There are a few different goals. For example, confidentiality, secrecy. This is saying that Eve cannot understand the messages. Integrity and authenticity. These say that if Eve tries to change messages or tries to pretend to be Alice, then Bob will figure that out. And we try in cryptography to make all of these properties: confidentiality, integrity, authenticity.
Now, you have encountered cryptography in your daily life when you're visiting a web page, assuming you're looking at the schedule of HITCON. You go into an HTTPS page and you can look at what cryptography is secure in your connection. But it's not very friendly to the user, because all you see there is 3 or 4 or 5 letter abbreviations, and well, here I've at least sorted those into 2 different types. So in cryptography we have 2 types of communication. We have cryptography with what we call symmetric keys. If Alice and Bob have met each other, they know each other, and they have a shared secret, they can use some from this upper category. And if they haven't met yet, like you're visiting a web page, you don't have any secret information that you share with this web page, so then you're using what is called public key cryptography, and here are the names of the public key crypto systems.
These cryptographic systems are designed so that even if somebody tries to figure out the secrets with a huge computer, this is a supercomputer in China, publicly announced supercomputer in China, the Sunway Taihu Light. I guess if you read the characters, it says something about divine power. And this is a very powerful computer. But even this computer cannot break the cryptography that we're using today.
Well, that is good for today. There's one problem, namely that in 1994, Peter Shor found an algorithm. And this algorithm has one requirement. It requires a sufficiently large quantum computer. This is a very, very large quantum computer. But given this quantum computer, his algorithm is able to break compute discrete logarithms and compute factorizations. So factorizations is just the normal, you have a product of two integers and it can break this into its two parts or multiple parts. Unfortunately, these two problems are the core of what we see on the internet in this category of public key cryptosystems. So his 1994 algorithm is a real threat to the cryptography on the internet, to the security.
But this is only a threat if somebody has a quantum computer. So, do we have quantum computers? Well, last year, Google proudly presented to the world a baby quantum computer. Okay, they didn't say it was a baby quantum computer. They said this is a powerful quantum computer. This quantum computer has achieved quantum supremacy. This means it does a calculation, one special calculation, faster than Taihu does the calculation. This is powerful for one calculation, and this is called quantum supremacy.
Well, but even though he looks very friendly in this computer, it's like nice, colorful Google colors. I mean, this can't do anything evil, right? I mean, it's pretty red and blue, and the guy looks friendly. However, he's pretty clear about the impact on security, the impact on cryptography that this research has. Maybe he is bragging a little bit too much, but he's saying in a 5 to 10 year time frame, quantum computing will break encryption as we know it today. So that is a strong statement about what these quantum computers will do in a rather short time frame, just 5 to 10 years.
Now, what about other countries? Google is building their computer in the US, so I looked around for trusted news from other countries, and I found a very reputable news site from China called globaltimes.cn. Maybe you've seen it yourself. And they say that Chinese researchers are going to jump ahead of Google. Of course, this is what the Chinese government wants everybody to know. Who knows what they're doing secretly? But this is their public announcement that China, this was an announcement in August, China is building a computer that publicly is as good as Google's quantum computer. What are they doing secretly? Who knows?
Well, so since we don't have any pictures of that, let's put just the quantum symbol on it. It's like when you're purchasing something on the internet and they tell you product details may differ. Well, this is our symbol image of a big, powerful quantum computer that nobody is believed to have right now. But let's go back to the slide that we had here, where I listed the different crypto systems. So if Eve changes into Eve with a quantum computer, then everything in the bottom part, everything under public key cryptography turns red. That means it gets broken by Shor's attack with a big, powerful quantum computer.
And what about these black things that weren't broken? Well, this is symmetric key cryptography. This was, again, where the Alice and Bob have met already, and Alice and Bob are sharing a secret key. And now cryptography can build very easy solutions, very easy ways to securely encrypt your data if you have a very long shared secret. And long means as long as the messages that you're sending. So if you've met somebody, Alice and Bob meet privately, and then they flip some coins, make some random numbers, and they exchange many, many random numbers. And then they can use what's called the one-time pad, and that will encrypt all of their data in a way that the attacker cannot figure out what the message means. And they can also protect integrity and authenticity. They can stop forgeries. It's a little more complicated, but it's called a Wegman-Carter MAC. And this is a mathematical computation which protects the integrity of your message. Nobody can fool Bob into taking another message. It's only from Alice. Now, what happens if you don't have a long secret key? Alice and Bob meet for just a few minutes, and then they don't have time to flip a million coins. What they can do is use AES. AES is a standard way to take a short secret key. For example, AES 256 takes 256 coin flips, 256 bits, and AES 256 makes a big, long, random string, which is like it can flip a million coins for you, a billion. And Alice and Bob, if they know the same 256 bits, they use AES and they get the same long shared secret. Anybody else who doesn't know the 256 bits, they have no idea what the AES output is. They could try guessing, but it takes a very long time to guess 256 bits. Now, the security of AES is something that people have studied for 20 years, and it's fine. AES 256 will never be broken, even with a quantum computer. If somebody has a quantum computer, they can use Grover's algorithm, which will make guessing faster, but it still won't break AES 256. If you're really optimistic about quantum computers as an attacker, maybe Eve thinks that Grover's algorithm will break AES 256 in only 2 to the 128 operations. But that's a very large number of operations. If you're using AES 128, then Grover's algorithm takes 2 to the 64 operations, and maybe that's a problem. But if you use AES 256, you're fine. AES 256 will never be broken.
Okay, so how about this other part? How about the part in public key cryptography where the quantum computer will break everything? So there is an area of research, and that's what the topic of this talk is, and that's called post-quantum cryptography. So post-quantum cryptography is cryptography under the assumption that the attacker has a quantum computer. So just as in our picture where we have Alice and Bob communicating, and in the middle, Eve has now turned into quantum Eve. So quantum Eve is the same Eve that we had before, still has the same interests, has the same eavesdropping desires, but also has a quantum computer. It typically doesn't mean that Alice and Bob have a quantum computer. For instance, Alice and Bob are communicating today. Eve is recording messages for later to break them with a quantum computer. That's one of the scenarios we're looking into with post-quantum cryptography. So Eve has a quantum computer, Alice and Bob do not. And so this research I had already shown you, the 1994 paper from Shore, then had mentioned a paper by Love Grover from 1996. So these are the two most visible algorithms. But there's a whole area of research called quantum algorithms or quantum computing, where they have developed many more algorithms, and several of those have relevance to cryptography. So if you want to learn more about quantum algorithms, there's a link called the Quantum Algorithms Zoo. So you can go there and click on them, and you'll find out that some of the algorithms are good for finding fertilizer or medication or weather forecasts. But then there also are some, definitely Grover and Shore, but also Cooperberg and several variations of those quantum walks and so on, which have effect on on cryptography. Now, it's not all lost. I showed you what is currently used on the internet, and that all turned red. But there were some systems even before these other ones came into use. They just were not as popular, but Shore's paper kicked off interest in figuring out what systems could remain secure against quantum computers. And so after like a few years, people were pointing out, hey, look, here is something which we believe is even hard for a quantum computer. So even if Eve has this quantum computer and it's a big quantum computer and so on, then Eve can't do anything against these particular systems. And so this area needed a name, and Dan here in 2003 wrote on a mailing list, how about we call this post-quantum cryptography? So it's cryptography for an area past the advent of quantum computers. But it just means that the attacker has a quantum computer. It does not mean that the user has a quantum computer. And while this was catching up, so within 3 years we had the first academic workshop. 2006 was the first international workshop on post-quantum cryptography, and that kicked off a longer series of conferences called Peak Crypto. So if you Google on the internet, you'll find Peak Crypto 2006, 2008. They were going basically every year and a half, and you see on the slides that the frequency has sped up a little bit. And if this talk makes you interested in this area, you're just in time to catch the 2020 edition in 2 weeks from now, which will be held online, because no other country other than Taiwan can actually have physical workshops right now. And in Taiwan, you can still participate in these workshops when they're online. Also, several standardization bodies have caught up. So NIST is the National Institutes for Standards and Technology. That is a body in the US, but it has turned, whether by historical accident or by pushing of certain nations, it has turned into the de facto standardization body for cryptography. So NIST defines what cryptography gets used broadly. And so in 2015, they hosted a workshop to kind of figure out, is there enough interest? And okay, the room wasn't nearly as big as this room, but it was like 120 people, which was more than the room could handle. So they had to close registration and they had to stream some stuff. So yep, they decided it's interesting and announced the next year that there would be a competition. And this competition has been running for the last few years and has kept many of us busy. And Dan is going to show a little bit of the details of that.
All right, so let's take a look at, here's the names of the...
Well, it's going to take a little bit of time.
Okay. So BigQuake. This is a code-based crypto system, and the authors were... Okay. I won't go through all of these, but just to give you the big idea, these are from 260 people. Actually, even more people submitted. When NIST announced they're running a competition, there were 82 submissions. These are only the 69 public submissions. NIST said these were complete, proper submissions. Maybe the other 13 didn't include software, or they made some mistake, they didn't follow the rules. But these 69 submissions from 260 people, all of these followed the rules, and they posted all of these, and this was the 21st of December, 2017. Now, by the end of 2017, 10 days later, there were 8 submissions that had been attacked.
Oops,
yeah. There are some of these that are in red, and those are broken. Broken means it's completely unsafe, don't use it. You cannot use, for example, HK17. And the ones that are underlined in red, which is all of these red ones, those had Python scripts which showed, here's how to break these proposals. Some of these were posted the same day or within a few days, but all of this was within 10 days of the submissions being public. The brown ones, those were not so serious attacks. It was maybe less security than they said they should have, but maybe still okay. And then, well, by the end of 2018, 1 year later, you see a lot more red, a lot more underlines. Okay, rank sign, this was a serious attack, but nobody wrote a Python script, so no underline. More brown ones with some loss of security. And then NIST said, okay, we're going to focus, we're going to have a second round of the competition with the most interesting submissions. And so they crossed out many submissions, and they selected 26 candidates. Now, some of these are in blue, and the blue ones are ones that merged. For example, ntrue HRSS and ntrue encrypt, those merged. Those turned into one submission. They're very similar, and they said, we'll just join the teams and work together. And there were a few different merges. And then, well, more attacks happened. There were 8 more attacks. Well, some of these were Gila 5 and Lida. These were, if I go back, these were already in brown before. But then there were 8 more attacks, some of them serious attacks. And then NIST said in 2020, just in July, they said, okay, we're going to focus on 15, the ones that we think are the most interesting, and these are the 15. Including some merges. So you see 17 names listed. And out of these, some of them are called finalists, and NIST is thinking about standardizing those in well, starting in a year or two, they'll select something. And some of them are alternates where they're saying they'll select some of those maybe in 3 or 4 years. Okay, and this is the current status of the NIST competition.
So you might not think that everything is kind of okay, NIST is doing something, and also when you look in other reports, so the National Academy of Sciences of the United States published a big report, so they got people together, several researchers invited, they had several researchers on the board to write this report. They invited some more for special sessions, so we ended up going there for a session on post-quantum cryptography and on the effects of quantum computers on cryptography. And then end of 2018, they published their report, including 10 key findings. Now, the first key finding, you might translate as, don't panic. The first key finding was, well, maybe a little bit contradicted by Google and maybe the Chinese, but they were saying we do not expect that anything will happen in the next 10 years that seriously threatens RSA 2048. So RSA 2048 is one of those 3-letter abbreviations that you saw on the previous slides, and it's a very common system that you will find when you click on the details in your browser. So if you're wondering what is securing your connection to the internet, this is one of the typical ones, and this report, with the basis of a lot of researchers, is saying, yeah, probably nothing for the next 10 years. But that's just the first key finding. It goes up to key finding 10, which I would say is more like panic. It ends with the nice words of saying the deployment of post-quantum cryptography is critical for minimizing the chance of a potential security and privacy disaster. These are academics writing about disaster. So this is serious news. This really means worry, do something. And the main point they highlight in this key finding 10 is that it takes a long time to roll out and to deploy post-quantum cryptography. And so even though it's still 10 years till quantum computer that big, that threatening would be existent, it is high time to do something. Here is another aspect that they don't put into a key finding, but they highlight in section 4.4, namely the effects on long-term security. So anything that you're sending today, yes, we said even the most powerful computer, the Chinese one is only number 4, there are 3 more computers which are more powerful, but even those computers cannot break our current cryptography that we're using today. They might find other weaknesses. Cryptography is often not the weakest part. So I'm not saying that everything on the internet is secure, but the cryptography is probably secure against today's computers. However, if an attacker is listening in today, if they're recording the messages today, and well, your messages are going over the internet, so of course they are public, they get routed around, and we have seen, for instance, in the Snowden revelations, that the United States is very active in recording the internet. I would be surprised if other governments are not recording the internet. So you should assume that everything you're sending today is stored somewhere. And even if it is encrypted, well, they can't read it today, but they might store it and decrypt later. So for future use, that means once they have a quantum computer, they can go back to today's messages. Anything that you send today, which is still interesting in 10 years when the attacker has a quantum computer, that is going to be lost. And that's a kind of strange time machine, because today you're feeling very sure, you're feeling secure when you're using the internet. And we tell you, yeah, don't worry, it's secure, the crypto is fine, but today's messages will become public in 10 years. And so it depends on what the world is like, whether what you're sending today is incriminating or not.
Let's look a little more at the other issue, the timeline for deploying cryptography. There are many, many steps that this takes. You might think it's very simple, like we have some crypto system and we've written down the crypto system and we put it in the web browser and we're done. But there are many, many stages that we have to do to make this work. Let me start at the top. At the top, we have to say, what are we trying to do? For example, confidentiality. We're trying to encrypt data. And then you have to figure out some mathematical transformation, some crypto system which achieves that goal, which is able to encrypt data. And then, well, maybe it's not secure. So you have to study algorithms that the attackers might use. You have to think, can somebody break this using a big computer? Maybe using a quantum computer in 10 years. And this you saw in the NIST competition. There were attacks against proposals from 2017, and there are attacks in 2018 and attacks in 2019, and actually there are even some new attacks now. So right now we're at stage 3. We're studying algorithms that the attackers can use. And we have to do this because we have to throw away the broken systems and only choose secure crypto systems. That's stage 4, where maybe we're getting to stage 4, but we're not really there yet. And even at stage 4, even if we have secure crypto systems, that's not the end, because we have to make these crypto systems usable. People have to be able to use the secure crypto systems in applications, which first means we need to have algorithms which compute these operations, the encryption or signatures, whatever operations. We need to have algorithms and software and maybe hardware, that's the next line here. We have to make that happen in a way that people can use and make it as fast as possible so that nobody complains about the performance. And then you think, okay, now we can put it in the browser. But it's not that easy, because the software is something that can be broken by timing attacks, for example. There are always new announcements about, the timing of some operation leaked some secret data, and now the attacker knows your secret key. So,
just the raccoon attack a few days ago was a timing attack.
Yeah, lots of these timing attacks breaking everything. And so you need software and hardware which does not leak information through timing and through electromagnetic radiation and acoustic signals. There's lots of side channel attacks. It's not so easy to just implement an algorithm securely. Once you know what all the attacks are, then you can choose the safe implementations, the secure implementations that correctly compute the function that you want to compute. And then maybe they're all too slow, so you have to throw away algorithms again. And if it's fast enough and it's secure, software or hardware, for a secure crypto system, then you can put it into the user application, which maybe the user says, oh, actually it doesn't fit. It's, even though it was fast enough and it looks good, they realize, no, that's not what I actually wanted. It doesn't work in my application. And so then you have to go back to the beginning and start over. This type of picture of having stages feeding into subsequent stages, this is called a waterfall. And waterfalls are never good, because when you have a waterfall, if you have a problem at the bottom, you have to go back to the top and start over. And, well, maybe you can fix it a few stages before, but it's much more efficient to think about the whole stack, to understand everything that's happening, and design at the top thinking about the rest of the picture. And every stage looks ahead to what's happening, and people talk to each other at the beginning. But that's a big project. It takes a lot of time. It takes many years to do all of this and to do it correctly.
All right, so that's what they mean by key finding 10 and the high time. Now, we don't have time to go into all the details of how these crypto systems work. We'll have one which we're going to show you some basis, but at least to leave you with some summaries of what these systems are, so that you know, like if somebody is trying to sell you post-quantum cryptography, then they should tell you what is the assumption behind these, what is the thing that the attacker is assumed not to be able to break. And so there are 5 big families of the public key systems that we study in post-quantum cryptography. And I've been narrowing them down to sometimes saying only encryption, sometimes saying only signatures. So encryption is the part that does confidentiality, signatures is the part that does integrity and authenticity. And some of these schemes could actually be used for both, but they're only really good for one of them. So for instance, code-based cryptography is an area I really like, but all the signature schemes that we have seen from there are not what you want to use. So I'm only saying code-based encryption. And so the highlight of this is that it has been around for a very, very long time. It is 1 year younger than RSA. RSA was the first public key system that is described as a public key encryption system from 1997, that is older than most people in the audience here. And then just 1 year younger is McAleese, who described a system that is based on what we call error correcting codes. So that's not codes as in implementation or codes as in secret language. This is codes as in adding redundancy so that when you're looking at a file and it has been, well, compromised, but just by errors, that you can recover the file. So that is what we call error correcting codes. And he noticed that you can turn the problem of decoding such codes into a crypto system. Hash-based signatures is what we're actually going to spend a few minutes on to explain. So that is another thing which has a very solid theory, also goes back to the 70s, and the benefits there are that the public keys are relatively small, and it has very few properties. I should also say for the McAleese system, one advantage is that the messages are very, very short. Public keys are large. Then isogeny-based crypto is a little bit the new kid on the block, so we're not so sure about its security. It has some very desirable features when you care about the sizes. So Dan was mentioning in this waterfall that at some point you might hit a block because it's too large. It doesn't fit into things. And code-based crypto, isogeny-based crypto, the advertisement is that what you're dealing with is relatively small. Overall, the smallest. Code-based crypto has shorter ciphertext but gigantic public keys. Code-based crypto, both the ciphertext and the public keys are relatively small. The hard
Isogenies.
I kept doing the same, thank you. So isogenies have small ciphertext and small public keys. And the security, now that's where you need a ton of mathematics to even understand what I'm saying. So there are mathematical objects called elliptic curves, and those you might encounter in a course of cryptography. Now, isogeny-based cryptography is doing some maps between different curves, and then the hardness assumption is that if you started on some curve and somebody just tells you the end of this computation, some other elliptic curve where you ended up, that it is hard to trace back how you could possibly get there. And from all we know, this is a problem which even a quantum computer can't solve efficiently, but it is a relatively new problem, so it is less well studied. It's a problem from the 2000s. Lattice-based cryptography is, well, kind of an overall pretty okay system, so you have small public keys, small ciphertext, and you can also use it for signature schemes. Similarly, smallish public keys, smallish signatures. It's kind of versatile, it's kind of everywhere. It is newer, so we're less sure about the security. And the hardness is finding something which is called a short vector in a lattice. And then multivariate quadratics. If you want to learn more about this, you are actually in the right country, because Boyin Yang, who was kind enough to announce us, is a world-leading expert in this area. And so there the advertisement is that it is a scheme where it has very short signatures, somewhat biggish public keys, so that's one of the downsides, and then the hardness relies on solving systems of equations. Now, you probably have seen systems that are linear and you're getting like 5x plus 7y is this, and you get another equation x and y, and you learned that this is easy to solve. What changes here is that they are not linear, not just x, but you also have an x times y, or you have an x squared or y squared, and a few more variables, a few more x and y's, and a lot more equations. And that is another hard problem, in this case, where a signature scheme can be based on.
All right, let's look at one of these in a little more detail. Inside signatures, first of all, what is the data flow in a signature? Well, Alice on the left side has a message, a picture or a document to send to Bob. And Alice also makes a secret key. That's the secret key all the way on the left. And then Alice also publishes something that everybody sees. Bob knows this public key, and also the attacker sees the public key. Alice and Bob do not share a secret. And now Alice uses the secret key and the message to somehow create a modified message, a signed message, to send through the network. And then that's received by Bob, and Bob uses the public key to extract the original message. Now, if Eve tries changing the message, corrupts the integrity of the message, changes the message to something else, then Bob, using the public key, will say, wait a minute, something went wrong. What's the right message? I don't know what the right message is. Somebody changed the message. So a signature system stops Eve from changing messages or making new messages. For hash-based signatures, the only thing you need is a good hash function. Every signature system that people use has a hash function. This is a function, a mathematical function that takes a message of any length and hashes it, well, does some computation, which produces, for example, 256 bits or 512 bits, some short, constant length string. Every signature scheme that we use has a hash function. Hash-based signatures, all you need is a hash function. Once you have a hash function, you can sign messages. And we'll actually show you a little bit of how that works. Quantum computers, well, Grover's algorithm can be used to reduce the security of hash functions, so use at least 256 bits or more, but then you're safe against quantum computers. And this is something which goes back also to the 1970s.
All right, so if you want to use something today and you don't want to just take things from the internet or from the NIST competition where you see things disappearing, here are some systems which are basically on the fast track. These have already been standardized, this time not by NIST, but by the Cryptoforum Research Group. So that is a part of the IETF, which is, well, the Internet Engineering Task Force. All right, these are the people who specify what your browser has to support in order to be allowed to go online, and what the servers have to be supporting in order to serve your browser the right cryptography. Now, I said before that NIST is typically setting the standards for internet. In this case, we had that the CFRG went ahead and said, here are some systems which are sufficiently well specified that we can standardize them. However, watch out, the caption doesn't say signature scheme, it has some extra words there. And those words are important. So it says that it's a stateful signature scheme. Now, stateful means that you must be able to count, that you have to remember basically what you have done. And it's not the normal data flow, not what Dan was showing, like there is a secret key and a public key. Stateful means you actually have a whole sequence or an array of secret keys, and you have to tick them off one by one. You have to remember, I have done 3 signatures. I've used the first 3 keys in my one secret key, and you have to remember this pointer. If you ever go back and reuse, say, the second key for a second signature, then the attacker can break it. The attacker gets too much information from that. So if you're in a situation where you can count, yeah, I know you all learned accounting even before you went to primary school, but your computer might not actually be as able to count as you think it would be. For instance, if you're using virtual machines, you might be storing your virtual machine, you're recovering your virtual machine from an image. Well, at that point, you're going back to the pointer it was at that point. Maybe you have done a few more signatures since, but since you restored from image, your pointer is back up here. So if you're in that scenario, you cannot use this. But other scenarios are, for instance, if you're a Debian developer and you're signing the code release, well, you better be able to count, you better know exactly where this key was used for a signature. So Debian was actually saying, yeah, we are interested in using this system, please give us a full specification, we would like to use this. And also, if you're on a smart card, like if you're working on hardware and you have some chip card, those also have memory which is able to, well, keep state to count. So if you're in that situation, here are 2 links, and the slides will be online. You can just click on those, which specify hash-based signature schemes with all the benefits that Dan was just saying, that they don't need anything other than a good signature, a good hash function in order to get a signature, and are post-quantum. Now NIST is doing in parallel to the competition a fast-track version of standardizing these schemes as well. So in this case, the CFIG went ahead, standardized them, and now NIST is saying, hey, okay, we're taking the same. They asked for a few comments, but we're expecting this standard to come out soon. Again, this is for stateful hash-based signatures. They're not full-fledged signatures. However, they are ready to use. And also ISO, which is International Standards Organization, has now a track on standardizing these hash functions or these hash-based signatures.
Let's look at just one example of how hash-based signatures work, and then we'll finish up. This is going to be complete signature code in Python for signing using hash-based signatures with one restriction. The restriction is we can only sign one message, the empty message. That might sound a little silly.
Yeah, that sounds useful.
Except if you think about it, actually that's very useful. Maybe you have an alert message. For example, you have one message which says typhoon warning on this date. And then you don't want somebody to forge that message. You want to be able to check, is this the real message from the right person, from Alice, with the right public key? And then you can have another public key for tomorrow and another public key for the next day. And so an alert message is something that should be signed for security. And also, once you understand how empty messages are signed, then it's actually not too hard to do longer messages, but we'll just do empty messages. So here's the key generation. Alice is taking some random data, the os.urandom, from the operating system. 32 bytes, 256 bits of random data, and hashing those with SHA-3 256, which is in hashlib, and well, okay, you have to have sufficiently recent version of Python to have SHA-3 256 in hashlib, and maybe say hashlib.SHA-3 256, but this is all built into Python. Python has the hash functions for you. And then the important point is the public key. Alice's public key is a hash of the random secret. And then Alice, well, remembers the secret and publishes the public key. As an example, here's, well, making one key pair from this sign empty, and it's just some random data is the public key, and some random data is the secret key. And the public key is a hash of the secret key. And this public key, Alice announces. Everybody knows this public key is from Alice. And now let's sign a message. The signature of the empty message is simply the secret. If Alice wants to say, okay, alert, Alice simply publishes the secret. And then if you want to check, has this message, has the empty message been signed, you simply take this signed message, the secret from Alice, and you hash it. And if it matches the public key, then okay, you've got the empty message. If it doesn't match, then you say bad signature. The only person who can sign a message is Alice, because Alice is the only person who knows that random secret with the right hash. Everybody can check, and Alice is the only person who can make a signature. And then, well, this is just using these functions, and if you sign the empty message, anybody can check, and they get the empty message back. If you try forging a message, you have to figure out the secret, or figure out some string which hashes to the public key. And until Alice reveals that secret, that's hard to do. You can only use this once, because then Alice has revealed the secret, and then it gets more complicated. So you should look at Tanya's lectures on hash-based signatures, and then you'll see how you can do more, sign more bits of messages, and sign arbitrary length messages. And this was actually from a mini school that was here in July. And okay, you'll finish it up.
So Just to give you some recommendations, these are absolutely unbiased, objective recommendations. These are the best post-quantum systems that NIST has in its round 3, which by definition are exactly the systems that we and our collaborators here in Academia Sinica submitted. So here are the links. These are one code-based system, so that is the encryption system going back to 1978. Rainbow is a multivariate signature system. There's Entro Prime, which is a lattice-based encryption system, and Sphinx Plus, which is a hash-based signature. So 4 of the 5 areas, and exactly the 4 which I said, have been relatively well studied. We have submissions in the last round of NIST, and we do think that these are the future. So if you want to settle on something before NIST finishes, this is our recommendation. But of course, you should take a look at more things, so we have a whole bunch of more information online. So please go there, please look, and, well, try to break, try to use, and see where that fits. Thank you for your attention.
有没有那个在场有没有任何问题？就是如果要用中文问问题，我们也可以代为翻译。后面好像有人举手，那个再举一次手好吗？哦，大概可能是我看错了。
We have some bonus slides. If you don't want to ask questions, we can keep you busy for several hours. We have slides for how to sign 1-bit message.
直接用你的麦克风。
We have slides for signing 2-bit messages, 3-bit messages, 4-bit. Okay, somebody has a question.
Did it work? Okay. You have mentioned that we have to panic because our message will be revealed in 10 years. As far as we know, our government is providing EID, which use RSA 2048 as the core. Do you suggest that the government to switch the system such that we can avoid the attack from the computers?
So I think for everything which is public key cryptography, for encryption, where you need to ensure secrecy, so confidentiality for more than 10 years, I would recommend trying to deploy post-quantum encryption systems. For signature schemes, it's a different story. Signature schemes matter at the moment when you check, when you verify whether the signature is valid. At that point, you must trust that nobody has a quantum computer. So at the moment, if you verify a signature, we don't believe that anybody has a quantum computer. So we do believe that right now, if you verify an RSA signature, it is actually a valid signature. So in that sense, you could say signatures are less urgent. We normally encourage people to already do use public key, so post-quantum signatures now, because typically you use signatures when you're working on operating system updates. And so if the signature system is your way to change the cryptography behind it, so if you want to use it in order to, well, update the system, then you must be sure that the attacker doesn't have a quantum computer yet when you're using it. And so you're getting into this, well, what comes first problem. So for that, it helps to actually have post-quantum signatures deployed. However, it depends on how long the lifetime of the product is. If it's a product like a passport is only good for 10 years, so if in those 10 years we don't believe a quantum computer will have the power to break a signature system, then the first batch of signatures, first batch of passports will still be fine. But at some point you run into issues where you have to make predictions about the future. Say passports in 5 years, you're making a prediction about the future in 15 years that the attacker doesn't have a quantum computer. And then it gets unclear.
还有其他问题吗？请直接
Test. Okay, we would like there are a few algorithms in the fourth or third round of the NIST competition, and one of them is from Sinica, and it's really the proud of Taiwan. I'm a student currently studying in cryptography, but I must admit that I understand almost nothing like those things on the slide. But we would still like to contribute, but we have no idea what kind of way can we contribute to the whole thing or to the algorithms that Sinica built. Like, is there any specs for us to follow, or maybe we can build help writing some codes on GitHub to do some maybe Go, Python, or Rust implementations, or even we can just a guess, we can contact like MTK or NND to build some specifically crafted instructions inside the CPU to make the cost of our Sinica algorithm more, in a sense, more cheap. Is there any other ways that you recommend us to contribute to the whole thing?
So, sorry? Sure, of course you can contribute by breaking some crypto systems, but you sounded interested in writing software.
Break the others.
Yeah, so long answer for how to get more information is, well, there's lots of links to follow. But the short answer, what you really should do, is talk to Yang Boyin here, because he is the master of making everything run fast, and he's been making multivariate quadratic systems and lattice systems and so on run really fast. And he has lots of projects, which are projects that you can start on. Some of them are projects that you need programming experience, but no particular cryptographic experience. And then there's more advanced projects if you're through the initial project. But it is very useful to have software that is implementing these cryptographic systems. And then there's more advanced challenges. For example, testing the software. It's not so good if the software doesn't work. And then there's actually verification systems. You can try to have the computer checking automatically that the software works. And there's more advanced things. But anyway, so talk to Boyin Yang, and he will tell you what the top priority projects are.
And let me add a little bit of advertisement. If you want to learn more about these systems, the last slide includes a bunch of links, and I'm still waiting for same person to come up with another URL, because the summer school he ran here in July also has recordings. And then, of course, we have a lot more time if we're only talking about hash-based signatures for a full hour.
Okay.
So we can go into much more detail than we could, covering the whole field of post-quantum cryptography and then trying to highlight one little piece. So, I mean, we do have some of the slides copied here, but there's a lot more information in the full slide set, and his summer school covered all the areas. And of course, we're also happy to take contributions for our systems, not just for Boyin's.
好，我们那个时间已经有点超过了，那所以有其他的问题的话，可以稍后再问讲者。那我们就谢谢两位这个专家。